Let's look at a basic situation where the coagulation cascade might be useful. Looking right here, we can see a basic representation of a blood vessel. We have our vascular epithelial cells lining the blood walls. And then inside the actual bloodstream, we have red blood cells in red, plasma proteins in blue, and platelets in green. So, what happens if one of these vascular epithelial cells is damaged? Well, first of all, immediately, blood will want to rush out this way as well, and we'll get a little bleed occurring. First thing that'll happen for the coagulation cascade is we get a little superficial plug occurring here of red blood cells and platelets. It gives us a bit of time to work with. So, eventually what we want to end up with is a little meshwork of protein that's connecting all these platelets and red blood cells together, kind of like rope holding together big rocks. So, how do we get this meshwork of proteins? It turns out this meshwork is a bunch of smaller proteins that like to stick to themselves. And this smaller subunit is known as fibrin. So, we need a way to make fibrin only active and stick to itself when we bleed. Unfortunately, fibrin in this form will always stick to itself, or other molecules of itself. So, as it turns out, our liver constantly releases an inactive form of fibrin, known as fibrinogen. So we need a way of converting fibrinogen into fibrin when we bleed. And when we bleed, there's another enzyme present which converts fibrinogen to fibrin, and that enzyme is known as thrombin. So thrombin converts fibrinogen to fibrin, which is kind of wordy and lengthy. So, to save time and space, we'll just say this. Thrombin leads to the production of fibrin. And that's really the case in most of the enzymes in the coagulation cascade. It's a bunch of inactive precursors being converted into an active form by an upstream protein, or a downstream protein, sorry.